Welcome to Spring LIB.
Okay, in this problem, we're going to be looking at the photoelectric effect. We're given light with a power of 2.5 watts and a wavelength of 124 nanometers, which ejects photoelectrons at kinetic energies of 4.16 eV each. We're asked to find the work function of this metal from which photoelectrons are being knocked out of place by the incoming light. We're also going to be asked for the number of these electrons per second being ejected by the incoming light, and we're going to be asked for how these scale with the power of our light and its wavelength. So the equations we're going to be using for this problem are the simple photoelectric effect equation, which simply says that the kinetic energy of the ejected photoelectrons is equal to the energy per photon of the incoming light minus the work function, the characteristic work function of our metal, which changes from metal to metal. We're also going to use we need to have the energy per photon of light, which is proportional to frequency and inversely proportional to lambda, which involves the Planck constant h and the speed of light in the case if we use the wavelength. In order to determine the number of electrons ejected from the metal, we make use of a statement in the problem prompt, which says that every incoming photon will eject its own electron. So if that's the case, then to determine the total number of electrons ejected, we can simply take the energy, the total power of our beam, energy per second, divide by the photons per second, and that will result in a number per second. Constants we'll need to use are Planck's constant. I have it quoted in electron volts seconds, which will be more useful than using it in joules per second. Because we're given kinetic energy in electron volts, we're asked for work function in electron volts, so it makes sense to be using electron volts for h. We also have the speed of light, which is approximated well by 3 times 10 to the 8 meters per second. Okay, so let's jump into it. So to start, we can use, because we're already given the kinetic energy per electron, and we're also given the wavelength of our light, we can set up the equation for the photoelectric effect. We can say that phi is simply energy per photon minus energy per electron. We can then express the energy per photon as hc over lambda, where we know these are two constants and lambda is given to us, minus k. We know all of these things, so we can now plug in some numbers and figure out what this work function is. Oh, using the wrong units for h. We will use the version in electron volts. And of course, the speed of light. All of this is over the wavelength of the light, which we are given to be 124 nanometers. And this, if you take a look at the units, you'll see that this whole quantity will give us something in electron volts. We're going to subtract the kinetic energy per photon, which is 4.16 eV. And we actually find that this whole quantity ends up being exactly 10 eV, which is somewhat convenient. Which will end up giving us a work function of 5.844 eV. One of the things we're asked to solve for. Great. So if we assume that every photon knocks its own individual electron, then the number of electrons being ejected per second should simply be the total power of our beam divided by the energy per photon in the beam. So we know the power of our total power of the beam, and we can use hc over lambda, substitute in for E, so we are left with lambda over hc. And this is going to be the expression we are analyzing. Notice that hc is constant. Power we can change, and wavelength we can change, which are both up top in the fraction. So if we simply plug in the numbers we were given, this will come out to be, we can plug in 2.5 watts, which is joules per second. We got to be careful there. Lambda 124 e to the negative 9 meters. And in this case, we have to use, because we are given watts in joules per second, not electron volts per second. We have a watt is defined as a joule per second. We have to use the Planck constant in joules per second, which in this form will be 6.626 e to the negative 34 joule seconds times 3 e to the 8 meters per second. And the result is about 1.55 times 10 to the 8 electrons. Or equivalently photons, because there's a one-to-one relationship. For every photon, we make an electron. That's the idea. So at the very end of this problem, they ask us, if we were to cut the power in half, how would this affect the number of electrons ejected? We see that because P is in the numerator of this fraction, if we changed it out for P over 2, it would simply cut this number in half. So cutting power in half cuts the number of electrons in half. Equivalently, we ask, what if we cut the wavelength in half? And we see, once again, because lambda's in this numerator, if we cut lambda in half, it would just simply cut the electrons in half. So that's the conceptual question answered. And that's everything we're asked for. We were asked for work function. We found it using the photoelectric effect equation. And we were asked for the total number of electrons ejected. And we can do that by looking at the total power of the beam divided by the power per photon, and assume that each photon ejects an electron. All right. Thank you very much.